Welcome to this coding walkthrough. In this video, we'll be tackling LeetCode problem number 1481, titled Least Number of Unique Integers After K Removals. This problem challenges us to minimize the number of unique integers in an array after a specific number of removals. It's a great opportunity to explore problem-solving strategies involving frequency counts, sorting, and optimization techniques. Let's dive in. In this problem, we are tasked with minimizing the number of unique integers in an array after removing exactly k elements. The input consists of two parts, an integer array called ARR and an integer k. The goal is to remove k elements in such a way that the remaining array has the smallest possible number of unique integers. For example, if the array has repeating numbers, removing elements strategically can reduce the count of unique integers left. The output is a single integer representing this minimum count of unique integers. This problem tests our ability to think about frequency of elements and how we can optimize removal strategies to achieve the desired result, all while adhering to constraints on the size of the array and the values within it. Let's go through the first example. The input array is 4, 3, 1, 1, 3, 3, 2, and k is 3. This means we need to remove exactly 3 elements from the array. To minimize the unique integers, we analyze the frequency of each element. 4 appears once, 3 appears 3 times, 1 appears twice, and 2 appears once. The optimal strategy is to first remove elements with the lowest frequency. So, we remove 4 and 2, which account for 2 of the removals, and then remove one occurrence of 1. The remaining array is 3, 3, 3, 1, which has only 2 unique integers, 3 and 1. Thus, the output for this example is 2. Now, consider the second example. The input array is 5, 5, 4, and k is 1. Here, we need to remove just one element. The array contains 5 appearing twice and 4 appearing once. To minimize the number of unique integers, the best choice is to remove the element with the lowest frequency, which is 4. After removing 4, the remaining array is 5, 5, which has just one unique integer, 5, therefore, the result is 1. This demonstrates that even with a small number of removals, choosing the right element to remove is critical to achieving the desired outcome. Finally, in the third example, the input array is 2, 4, 1, 8, 3, 1, 2, 2, 1, and k is 4. Here, we need to remove 4 elements. The frequencies are as follows: 2 appears 3 times, 1 appears 3 times, and 4, 8, and 3 each appear once. To minimize unique integers, we start by removing elements with the lowest frequencies. First, we remove 4, 8, and 3, which account for 3 removals. For the fourth removal, we reduce the frequency of 2 by 1. The remaining array is 2, 2, 1, 1, 1, which has 3 unique integers, 2 and 1. Thus, the output is 3. This example highlights how balancing frequency reduction and strategic removal leads to the optimal solution. Additionally, the problem's constraints ensure efficient processing even for large arrays, and edge cases like k equals 0 or k equals len, are crucial to consider when solving the problem. To solve this problem, we're aiming to minimize the number of unique integers left in the array after removing exactly k elements. One approach to consider is the brute force method. The intuition here is straightforward: we would remove every possible combination of k elements from the array, then count the number of unique integers left in each case, and finally return the minimum. However, when we look at the implementation, this involves generating all possible combinations of k removals, modifying the array for each combination, and calculating the number of unique integers repeatedly. The major drawback is the exponential growth in the number of combinations as the array size increases. For an array of size n, this approach has a complexity of O, C, N, K, *n, which becomes computationally infeasible for larger inputs. While it's conceptually simple, this trade-off in efficiency makes it impractical for real-world scenarios. A much more efficient approach is the optimized frequency-based method. The key insight here is that to minimize the number of unique integers, we should prioritize removing elements that occur the least frequently. By focusing on these less frequent elements, we can maximize the reduction in unique integers. To implement this, the first step is to count the frequency of each integer in the array, which can be done using a dictionary or a counter. Next, we sort the unique integers by their frequencies in ascending order. Once sorted, we iterate through the list, removing elements and decrementing k by the frequency of each removed integer until k is exhausted. Finally, we count the number of unique integers remaining. The complexity of this approach involves counting frequencies in O, n, sorting in O, U asterisk log, U, where U is the number of unique integers, and iterating through the frequencies in O, U. This gives us an overall complexity of O, n plus U asterisk log, U, making it both efficient and scalable for large inputs. Another variation is the heap-based method, which uses a min-heap instead of sorting to extract the least frequent elements efficiently. The heap-based approach operates similarly to the frequency-based method but with a slight variation. Here, after counting the frequencies of elements, we insert these frequencies into a min-heap. The heap lets us efficiently extract the least frequent elements, and we continue removing elements and reducing k until it runs out. Once complete, we count the remaining unique integers in the heap. While the time complexity is similar to the sorting-based approach, at O, n plus U asterisk log, U, the heap introduces additional memory usage. This makes it slightly more memory-intensive than sorting, but it can be useful in scenarios where frequent updates to the frequency list are required. After considering both methods, the optimized frequency-based approach stands out as the better choice overall. Its simplicity and scalability make it easier to implement and debug. Sorting the unique integers by frequency provides a clear way to make optimal removal decisions without the overhead introduced by a heap. The heap-based approach, while efficient, is more complex and only necessary for cases involving dynamic updates. When comparing the trade-offs, both the sorting-based and heap-based approaches offer similar time complexities. However, sorting is simpler to implement and debug, making it the preferred method for most scenarios. On the other hand, the heap-based approach is better suited for situations where the array or frequency data requires frequent updates or dynamic modifications. In conclusion, the optimized frequency-based approach strikes the right balance between clarity, efficiency, and scalability for this problem. Its straightforward implementation and strong performance make it the ideal choice. By focusing on removing elements with the smallest frequencies first, we can achieve the goal effectively while keeping the solution clean and manageable. To minimize the number of unique integers in an array after removing exactly k elements, the first step is to count the frequency of each integer in the array. This gives us a clear picture of how many times each number appears. For instance, if the array is 4, 3, 1, 1, 3, 3, 2, the frequencies are 4, 1, 3, 3, 1, 2, 2, 1. Once we have this frequency count, the next step is to group integers by their frequencies. Here, the integers that appear once, twice, or 3 times are grouped together, resulting in 1, 4, 2, 2, 1, 3, 3. This grouping helps us decide which integers to remove in the most efficient way. Now, with the integers grouped by their frequencies, the next step is to sort these groups by frequency in ascending order. This ensures that we deal with the integers that appear the least first, as removing them has the maximum impact on reducing the number of unique integers. For example, the sorted frequencies are 1, 2, 3. From here, we proceed to remove integers greedily. Starting with the smallest frequency group, we check if k allows us to remove all integers in that group. If it does, we subtract the corresponding k value and move to the next group. However, if k is not enough to remove an entire group, we remove only as many integers as k allows and stop. For instance, if k equals 3, we can remove both integers in the frequency 1 group, 4 and 2, leaving k equals 1. Then, we partially remove from the frequency 2 group, removing one occurrence of 1, which exhausts k. At the end of this process, the remaining integers are 3, 3, 1, 1, and the count of unique integers is 2. The key to this approach lies in the greedy removal strategy. By prioritizing integers with the smallest frequency, we maximize the reduction in the number of unique integers while using the least possible k. Sorting the frequencies ensures that we always process these low-frequency groups first. Additionally, the ability to partially remove integers from a group ensures that no k is wasted, allowing for optimal usage. To implement this efficiently, we rely on data structures like a counter for counting frequencies in O, n, time and a dictionary to group integers by frequency for quick access. For dynamic processing, a min-heap or sorted list can be used as an alternative to manual sorting. Breaking down the complexity, the time required to count frequencies is O(n), where n is the size of the array. Sorting the unique frequencies takes U*log U, where U is the number of unique integers. Removing integers is U, leading to an overall time complexity of O(n) plus U*log U. Space complexity is O(n), as we store the frequency counter and group dictionary. For edge cases, if k is greater than or equal to the array length, all integers can be removed, leaving 0 unique integers. When all integers have the same frequency, the algorithm simply removes them in any order until k is exhausted. If k is 0, no integers are removed, so the unique count remains unchanged. Finally, for a single element array, the result is 0 if k is at least 1, or 1 if k is 0. This implementation solves the problem of minimizing the number of unique integers after removing exactly k elements. First, we count the frequency of each integer in the array using counter, which is efficient for tallying occurrences. Next, we sort these frequencies in ascending order, ensuring we can remove the integers with the smallest frequencies first, which minimizes the reduction in unique integers. In the main logic, we iterate over the sorted frequencies. For each frequency, we check if k is large enough to completely remove that group of integers. If yes, we subtract the frequency from k. If k is too small to remove the next group, we stop the process. Finally, the number of unique integers remaining is calculated as the total unique integers minus the number of groups removed. The solution efficiently handles edge cases like when k is larger than the total array size, ensuring correctness. This is the Java implementation for LeetCode problem number 1481, least number of unique integers after k removals. The code mirrors the Python logic using Java-specific constructs. We use a hash map to count frequencies, sort them, and reduce the smallest frequencies iteratively to achieve the desired result. Note the use of Java's collections framework for handling lists and sorting. In this example, we are given the array arr equals 4, 3, 1, 1, 3, 3, 2, 4, and k equals 3. The goal is to remove elements from the array in such a way that we are left with the least number of unique integers. First, we calculate the frequency of each integer in the array using the counter class, which gives us 4, 2, 3, 3, 1, 2, 2, 1. This tells us that the integer 4 appears twice, 3 appears 3 times, 1 appears twice, and 2 appears once. Next, we sort these frequencies in ascending order, resulting in 1, 2, 2, 3. This allows us to prioritize removing the integers with the smallest frequencies first. Now, we start removing elements, beginning with the integer that has a frequency of 1. Removing this integer decreases k to 2. Then, we remove the next smallest frequency, which is 2, and this reduces k to 0. At this point, we have used up all of k, so we stop removing elements. With k reduced to 0, we proceed to count the remaining unique integers. The frequencies left are 2, 3, which correspond to 2 unique integers. Therefore, the output for this example is 2. Now, let's consider another scenario where all elements in the array are removed. Here, the input is arr equals 5, 5, 4, and k equals 3. First, we calculate the frequencies of the integers, which results in 5, 2, 4, 1. This means that 5 appears twice and 4 appears once. We then sort these frequencies in ascending order, giving 1, 2. By focusing on the smallest counts, we can determine the sequence of removals. We start removing elements with the smallest frequency. The integer with a frequency of 1 is removed first, reducing k to 2. Next, we remove the integer with a frequency of 2, which brings k down to 0. At this point, there are no removals left to perform since k is fully used. Looking at the remaining frequencies, we see that there are none left, meaning there are no unique integers remaining in the array. As a result, the output for this example is 0. Let's now examine a partial removal case, where k is not large enough to remove all occurrences of a certain frequency. In this case, the input is arr equals 1, 1, 2, 2, 3, 3, 4, and k equals 2. First, we calculate the frequencies, which are 1, 2, 2, 2, 3, 2, 4, 1. Once we have the frequencies, we sort them in ascending order, resulting in 1, 2, 2, 2. The smallest frequency is 1, so we remove the corresponding integer, which reduces k to 1. At this point, the next smallest frequency is 2, but since k is now 1, we cannot fully remove any of these integers. This means we stop here. The remaining frequencies are 2, 2, 2, which correspond to 3 unique integers. Thus, the output for this example is 3. By following this structured approach of counting frequencies, sorting them, and removing elements based on the smallest counts, we can effectively solve the problem for any input. To analyze the time complexity of our solution, let's break it into its main components. First, we count the frequencies of integers in the array using the counter function. This operation involves traversing the entire array once, which takes n time, where n is the length of the input array. Next, we extract the frequency values and sort them. Since there are at most u unique integers in the array, this sorting step takes u*log u time, where u is the number of distinct elements. Finally, we enter a loop to remove elements based on their frequencies, reducing k as we go. In the worst case, this loop iterates through all u unique integers, which adds u to the overall time complexity. Now, combining all these steps, the total time complexity is determined by the dominating term. The sorting operation, which takes u*log u, dominates the linear frequency counting in iteration steps, which add up to n plus u. As a result, the overall time complexity is n plus u*log u. On the space complexity side, the counter object is used to store the frequency of each unique integer, requiring u space. Additionally, the sorted list of frequencies also takes u space. Beyond this, any other auxiliary variables contribute only 1 space. Thus, the space complexity is primarily determined by the storage of the frequency dictionary and sorted list, resulting in u. Considering the total space complexity, we can confirm that it remains u, as the space is dominated by the frequency dictionary and sorted list. Now, let's discuss the best, average, and worst-case scenarios. In the best case, if k is large enough to completely remove all elements with the smallest frequencies, we still have to perform frequency counting, sorting, and iteration, so the complexity stays n plus u*log u. Similarly, in the average case, all steps remain consistent, maintaining the same complexity. Even in the worst case, where k is very small and only a few elements are removed, the algorithm still performs these operations, so the time complexity remains n plus u*log u. To put this into perspective, let's compare this approach with a naive solution. A naive approach might involve repeatedly removing one element at a time, recalculating frequencies, and determining the remaining unique integers. This would require k*n time in the worst case, as we would iterate over the array k times. In contrast, the optimized solution avoids such inefficiencies. By counting frequencies once in n, sorting them in u*log u, and iterating over the sorted list in u, we eliminate redundant operations. This optimization ensures that the solution is much more efficient than the naive approach. Finally, let's solidify our understanding with a mathematical proof for the big O complexity. Counting frequencies involves a single pass through the array, which takes n. Sorting the u unique frequencies takes u*log u, as sorting dominates the cost compared to a linear traversal. Iterating through the u unique elements adds u. When we combine these terms, the total complexity becomes n plus u*log u. Since u is always less than or equal to n, the complexity simplifies to n plus n*log n for large arrays. On the space side, storing the frequencies of u unique integers requires u space, which is the final space complexity of the solution. When tackling this problem, there are a few common pitfalls to be aware of. First, sorting the entire array unnecessarily is a frequent mistake. Many solutions attempt to sort the array when the focus should really be on the frequency counts of elements. Sorting the entire array increases the time complexity to n log n, whereas using a frequency map combined with a min-heap allows us to remove elements with the smallest frequency efficiently, resulting in a faster solution. Another common issue is neglecting edge cases. For example, when k equals 0, no removals need to be made, or if k is larger than or equal to the length of the array, all elements are effectively removed. Failing to account for these scenarios can lead to incorrect results. Additionally, some mistakenly use a max heap instead of a min heap. A max heap prioritizes the highest frequencies, which is the opposite of what we need. Instead, a min heap ensures we can target and remove the least frequent elements first, aligning with the problem's requirements. Another frequent mistake is modifying the array directly during the removal process. For instance, using operations like remove repeatedly introduces inefficiency due to their high time complexity. Instead, leveraging a frequency map alongside a heap allows for much more efficient tracking and removal of elements. It's also crucial to validate input constraints. If constraints like 1 equals k equals len, are not respected, or if it's assumed that the array always contains unique elements, runtime errors can occur. Ensuring the solution is robust against invalid inputs is key to avoiding these issues. By focusing on frequency maps and adhering to constraints, you can create a solution that is both efficient and reliable. In an interview setting, it's helpful to focus on a clear and efficient approach. A combination of a frequency map and a min heap is commonly used. Start by calculating the frequency of each unique number in the array, then use a min heap to efficiently remove the least frequent elements in k steps. This approach minimizes the number of unique integers while maintaining optimal performance. It's also important to understand the trade-offs in time complexity. Sorting the frequency counts has a complexity of n log n, whereas using a min heap reduces this to n log u, where u represents the number of unique elements. Make sure you can explain this optimization clearly. Edge cases often come up in interviews, such as when k is 0, k equals the array length, or when multiple elements share the same frequency. Be prepared to articulate how your solution handles these scenarios. A good real-world analogy for this problem is resource allocation or inventory management, where the goal is to minimize the number of distinct items after a certain number of removals. This problem is closely related to several others that also employ frequency-based analysis and heap data structures. For example, LeetCode 692, top k frequent words, focuses on retrieving the k most frequent elements rather than minimizing unique integers. Similarly, LeetCode 347, top k frequent elements, deals with finding the k most frequent elements while using similar techniques like frequency maps and heaps. Another related problem is LeetCode 451, sort characters by frequency, where the goal is to sort elements based on their frequency, aligning with the frequency analysis required here. Finally, LeetCode 973, k closest points to origin, involves using heaps to efficiently select k elements, though the criteria in that case is distance. Exploring these problems can deepen your understanding of frequency-based techniques and heap operations. There are several alternative approaches to solving this problem, each with its own trade-offs. The sorting-based approach involves sorting the frequency array and removing elements with the smallest frequency until k is exhausted. While this method is simple and intuitive, it has a higher time complexity of n log n, making it less efficient for larger inputs. Another option is the bucket sort approach, which groups numbers by frequency and processes these groups in ascending order. This method is more efficient, with a time complexity of n, but it requires additional space and can be less intuitive compared to heap-based solutions. Lastly, there's the greedy approach, which involves directly iterating through the frequency map and removing frequencies in ascending order. While this approach can work, it's often less structured and may not handle all edge cases as effectively as solutions that rely on heaps. Carefully choosing the right approach based on the problem constraints is critical to balancing efficiency and simplicity. Great job! To recap, we used a frequency-based approach to solve this problem efficiently. Key takeaways include understanding how to prioritize removals and optimizing for edge cases. Thanks for watching, and don't forget to like, subscribe, and share for more coding content. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!